nice school and the following workshop, and also thank all the students and postdocs for coming here. And also the first time I visited Brazil, and I really already enjoy it. And so I'm giving this lecture about halo nuclei clustering and universality, and it will be, I'm planning to divide this by three sessions. So the first the first class will be about some general ideas about the structure and the properties of halo nuclei. And then we will move to the next two sessions about universality and how to use effective field theory to describe those universality in halo nuclei. And I'm planning to divide this into perspective from the two-body perspectives and also from the three-body perspectives. There are a list of those references that I used to prepare the slides, and also I think it might, for you, it might be interesting to read some of those review papers. I think this will you'll have a more detailed idea about the talk I will give today, and also for tomorrow. So for the we know that the in our universe, the different isotopes or different elements have different abundances, and this is related to the nuclear synthesis processes. And we know that for those very light elements, they are produced in the Big Bang nuclear synthesis, so happening at the very beginning of the universe. And so this will produce hydrogen, helium, and probably lithium, and also a few heavier elements. But most of those heavier elements are produced in this stellar nuclear synthesis, basically based on a stellar environment. And you can see that this abundance correlated with the binding energy per nucleon for those different elements. That would tell you why this trend is going down after the iron isotope. So we know that in this for this nuclear charge, different isotopes are produced in this stellar in the nuclear synthesis in different environments. For those very light elements, we mentioned that it is due to the Big Bang nuclear synthesis, and it can also caused by the cosmic ray reactions. And for those neutron-rich elements, it's for the S process, it's a slow neutron capture process. It's happened at this AGB star environment. And for those rapid neutron capture reactions, it was caused by the supernova and also neutron star mergers happening in the universe. And we also, in this nuclear charts, we also have proton-rich nuclei, and they are caused by the sun-like star and merger with a neutron star, so the binary systems. It will create a proton-rich environment that can help you to create those proton-rich nuclei. And so this is our nuclear chart again, and one specific nuclear isotopes are called this halo nuclei. And the definition of halo nuclei is that they have either neutron clouds, a diffuse neutron clouds, or a proton clouds extending very far beyond the core. And if you describe it in a clustering pictures, it has a tightly bound core surrounded by a few valence nucleons that are far away from the core. And those valence nucleons are loosely bounded. And so in this plot, we can see that you have either two proton halos, two neutron halos, 4 neutron halos, and 1 neutron halos. And also on the proton-rich line, you have this 1 proton halo and 2 proton halos that exist in the nature. And for those halo nuclei, they exhibit some specific, they're very interesting characteristics. They have extremely large matter radii compared to the usual A to the 1/3 power scaling laws. This A is related to the mass number of the nuclei. And those valence, the last few valence nuclei for the halo nucleus are weakly bound, or they produce either a weakly bound resonance state, bound state, or a resonance state close to the threshold. And for those valence nucleons, they normally occupy low angular momentum states, either S wave or P wave. It's really hard to find a D wave state or even higher partial wave states happening in halo nuclei. And for those halo nuclei, they also have enhanced cross sections in astrophysical reaction at finite temperatures, because those are really loosely bound states or resonance states. So normally in the environment on Earth, you can hardly find those elements. But if you increase the temperatures, because of the statistics, you can have higher reaction rates that for them to create. So this is why it's important in nuclear synthesis. And so I already mentioned that you have different groups of different halo nuclei, and divided by its valence neutron numbers and proton numbers. So we will talk about those different halo nuclei in the following lectures. And so besides halo nuclei, there's also another interesting clustering that happens in the nature related to the alpha clustering. One example is the Hoy state in carbon-12. It's an excited state, 0 plus excited state above the 3 alpha threshold. So it's a resonance state. And in the nature, it has, we know that to create carbon-12, you can have two processes, either 2 alpha create a beryllium 8 and then absorb another alpha that's to create carbon-12, or you can have a direct triple alpha reaction to directly create this carbon-12 state. And the existence of the Hoy states will explain the missing gap between the A equals 5 and A equals 8 in the primordial, or called the Big Bang nuclear synthesis. So this is really important to explain the nuclear abundance in the nature. We know that the halo nuclei was first observed in LB and L lab by Tanihata-san, and he measured the anomalously large interaction cross sections for light neutron-rich nuclei, and this paper was published in 1985. So it's exactly 40 years from now. So this year is actually an important year for us to discuss about halo nuclei again. And an example is helium-6 and helium-8 or lithium-11 that they have an enormously large interaction cross-section. So to understand this interaction cross-section, you can write this approximately into this simple formula. So it's related to the radius of the projectile particle, so the halo particles, and also the target particles. So if you combine these two radius and square times pi, you get the approximate number for this interaction cross-section. So we already know how large the target is, right? So you can use the measured interaction cross-section to help you to determine the size of this projectile particle. So it will, in the measurements, they found that they use different isotope beams to hit this target, and measured its interaction cross-section. They find that for these lithium isotopes, at lithium-11, there is a big jump from the normal size. So lithium-11 have a really large interaction cross-section, and this can tell you that lithium-11, right? Lithium-11 has a extremely large size compared to other stable lithium isotopes. So the name of this halo, I think, was first mentioned by this paper by Hansen and Johnson. They proposed this neutron halo structure to describe experimental observables. so this is probably the first time we use this name halo for describe those exotic nuclei. And there are also experimental evidence by finding this narrow momentum distributions and also enhanced electromagnetic dissociation cross-sections. And also from the atomic spectroscopy, you can also measure the charge radius for those nuclei, and they can find some large charge radius for those halo nuclei, and those are some evidence for determining the halo, to describe what is a halo nuclei. So, and those actually the halo nuclei are produced. We know that they're produced in the labs, and there are in the world there are many labs that are studying the rare isotope beams that can help you to create those halo nuclei. And I think this is an incomplete list, but it would tell you like it's quite spread across the world. And so basically, to produce those rare isotopes, there are two mechanisms, and I think probably for the talk on Thursday by Nakamura-san, he will talk about more experiments. So I just give you a heads up. And so one mechanism is use this in-flight fragmentations. So basically, you have a heavy projectile, so it's a heavy beam hitting also probably a medium mass or heavy target. So this can create it can create this distorted fragmentations and at quite high energies. So this fragmentation will then evaporate to create some light elements. So the halo nuclei can be created in this way. So, and for this mechanism, they will create medium or high momentum beams that can be used to study the halo nuclei at relatively large momentum transfer. And another way is to use this isotopic separation online mechanisms. So you have a light projectiles hitting a heavier target. So this will excite these targets, right? They combine together to a compound nucleus, and then this compound nucleus will decay to different fragments, including the halo nuclei. And the produced beam will be at low momentum. So you can use this to study some low momentum reactions, and including some precision measurements, because you can, for example, you can also trap those halo nuclei and perform experiments such as the mass evaluation or the atomic spectroscopies to measure its charge distributions. So, and this is a map for the production of those different isotopes that use different mechanisms to make those different different nuclei. I think so my talk will just, in this talk I will just briefly mention this, and I will skip the details about how to produce each element. And so to understand why the halo has an extremely large radius, we can use a simple quantum mechanics way to understand it. For the normal nuclei, the nucleon distributions is well described by these Wood-Saxon potentials. So you have a constant term plus this exponentially decay tail. So it's plotted on this figure on the right, and so there is for this exponential term you have R minus capital R. So this capital R is related to the size of the normal nuclei. It's basically scale with a constant 1.1 times the mass number to the power 1/3. And this the number in the bottom is called the diffuseness. So basically tells you how widely spread the nucleon distribution is. And rho 0 will give you the central density at R equals 0. So you can plot this at different mass numbers. You can see that if the mass number increases, the nucleus will then spread it. The nucleon distribution will then spread it further. And if you use this density distribution to calculate its root mean square radius, you will get these plots on the left. And so you can see that, so this is shown by this orange line here. So you can see that this distribution, how it grows with the mass number A. And you can compare that with the normal definition basically based on the liquid drop model, right? So it's 1.1 times A to the power 1/3. So it's showed by this red line. And although they have some discrepancies, but basically the growing trend is about the same. So it's in the same shape. So now let's use quantum mechanics formalism to describe how the nucleon distribution is. So you can suppose this one nucleon is in this radial square well potentials. So for the inner part, when R is smaller than a radius, capital R, it feels attractive potential. And when it's moved beyond this potential goes to 0. And so basically you can find the solutions for the wave function, S-wave function, for the inner part and the outgoing part. And so, but times some prefactors, right? So I will leave this as an exercise to how to derive these prefactors. And basically then you can use the matching the boundary conditions for the inner part and outside part to obtain those prefactors, and also help you to determine the binding momentum related to the potential well. So after solving that, you get this prefactors. So this is already the result. So we will try to derive this in the exercise. And but you can see that for the inner part, it's a sine times kappa r. It's oscillating potentials. So basically it goes from 0 to increase it to the boundary. And for the outside part, it's exponentially decaying, right? And if you pay attention to the outside parts, that these prefactors will then be related to the asymptotic normalization coefficients for the nucleon for the wave functions. And if this binding momentum gamma is times R is a small number, you can do a Taylor expansion on this quantities and obtain this square root of 2 gamma over 1 minus gamma times R. And in the later parts, we will use halo effective field theory to describe the asymptotic normalization coefficients. You will see very similar equations shown in the halo effective field theory. So then now we have the wave functions, right? So we can use these wave functions. Then you square it, you get the density distribution for this single nucleon, right? So it basically has this exponentially decaying part times some constant pieces. And you can use these densities, then calculate the root mean squared radius, and you obtain this number related to the binding momentum squared times the prefactor. This prefactor we mentioned, this is related to the asymptotic normalization constant. And basically it tells you that how the range corrections will come in. And so from these equations, now we see that since the binding momentum is related to the one nucleon separation energies, if the nucleon separation energy is small, then the binding momentum is small. Then if you look at this term, you will see that you will have a long-range tail for these nucleon distributions. So this is why the valence nucleon is far away, because its binding momentum or neutron separation energy is very low. So and you can see that for stable nuclei, it's basically the binding per nucleon is about 6 to 8 MeV. So if you use this formula, you will see that it has a rapidly falling down tail, right? But if you apply the binding for this valence nucleon about 1 MeV, then you get a quite extended tail, right? So it tells you why this valence nucleon is far away from the core. Okay, so now we just talk about the S-wave problems, right? But if you move to higher partial waves, you have these centrifugal barriers from the angular momentum. And it was solved by Riesager in this early papers that he showed that the root mean square radius as a function of the binding energies for different partial waves. And for S waves, you can see that if this neutron separation energy goes to 0, then its root mean square radius will go to infinity. So it blows up with the decrease of the binding energies. This is similar to what we see in halo nuclei, right? If you have really small binding energies, then the last valence nucleon is far away from the core. But if you go to higher partial waves, for P wave, it's also diverges at when E go to 0, but this divergence is slower than S wave. And then you move to D wave, you will see that this root mean square radius will go to a constant even when the binding energy, the neutron separation energy go to 0. So it tells you that it's really hard to produce a halo structure for higher partial wave states, right? So that's why normally what we see in halo nuclei are low partial wave, partial wave angular momentum states. And the reason is that because this higher centrifugal barriers at high angular momentum will prevent the wave function to extend further, right? So this is a list of different one neutron halo isotopes and shows their neutron separation energies. You can see that some of them have a bound state, and for beryllium-11, it also have a first bound excited states. The binding energies for those valence nucleons are really low. Some of them are even smaller than 1 MeV. And you also have this lithium 8 or lithium 10 that has a S-wave virtual state. And let's see that. And now if you move, also for the helium-5, it has a P-wave resonance state. So let's just show you different types of one neutron halos. And for some of those one neutron halos, if you add one more neutron, you will have two neutron halos. So we'll discuss some of those properties in details in the following few slides. So besides those one neutron halos, there are also two neutron halo nuclei that can be seen in the nature. And for those two neutron halo nuclei, there are basically two types. There's one type that basically for those two neutron halos, you have a tightly bound core surrounded by two loosely bound valence nucleons. So let's now focus on two neutrons, for example. And for one type, this neutron and core form a bound state. And then if you add one more neutron, it also form two neutron bound states. So examples are beryllium-12, carbon-20, and this calcium-62. But there's also a different type of two neutron halos that form a called Borromean states, where this neutron and core is not bounded. So it's either in a virtual state or in a resonance state. But surprisingly, if you add one more neutrons, this two neutron and the core will form a three-body bound state. So this name Borromean state was first mentioned in the symbol for the house of Borromean family in Italy, and was later used this name to describe this three-body states. So for this picture, you see that the Borromean has three rings, right? If you move one ring, the other two can be detached, right? So only when you put the three rings together, they bonded to a three-body states. And this is similar to what we see in these two neutron halos. And I just want to show you an interesting picture. So this is a picture that was shown in this Uffizi Galleria in Florence, and was a famous picture called Pallas and the Centaur. So the goddess and this centaur, so half man, half horse beast, right? So this is a painting by Sandro Botticelli. So I happen to find that if you look closely to the clothes on this goddess, you will find this three-ring Borromean states and also four-ring Borromean states, right? So this is actually the symbol, not for the Borromeo family, but for the House of Medici family. So this family owned this Uffizi Gallery in Florence. So I think this is interesting. So now let's talk about how to solve this two neutron halo systems in a quantum mechanics way. And so before we talk about three-body system, let's talk about two-body system first. For the two-body systems, when you need to solve these Schrödinger equations, you write down this kinetic term plus the potential terms, two-body interactions. So then you can use spherical coordinates to describe these Schrödinger equations. Then you have this kinetic term can be written as the radial part plus angular momentum part, basically L squared over R squared. And then for this angular momentum part, it has some eigenstates. Those eigenstates are related to this called spherical harmonics, right? So you can have this spherical harmonic states with eigennumbers L times L plus 1. So this will then turn into a number. And then the full wave function can be expanded in this spherical harmonics basis. So then you have the full wave functions. The radial parts of the wave function is related to the radial part of the kinetic energy plus this angular momentum part into radial functions plus the two-body potentials minus its eigenenergies. So once you solve these equations, you get the binding energies and also the wave function for these two-body problems. So this is, I think, this is the normally you can see how to do this in quantum mechanics textbook, right? So now let's move to the three-body problems. And for the three-body problems, so first of all, what we want to do is you have three particles. In general, you have each particle has three coordinates, right? So 9 degrees, totally 9 degrees of freedom. But you need to remember that there are three coordinates that are independent of the structure of these three-body systems. That is the center mass motions. So once you remove the center mass motions, you have left with 6 coordinates, right? So the most convenient way is use Jacobi coordinates to describe the six dimensions. So first, you write down this distance from one particle to another particles, and then you from the center mass of this pair to the third particle, you have another distance. So this two different eta 1 and eta 2 will give you these 6 dimensions, right? So and then we transfer this into called hyperradius hyperspherical coordinates. So in this hyperspherical coordinates, there's one quantity called hyperradius related to basically the overall size of these systems. So you have eta 1 squared plus eta 2 squared, and all the other 5 coordinates are called the hyperangles. So you can use this to describe the orientation and also the shape of these three-body systems. So the first 4 coordinates related to the angles of eta 1 and eta 2, so basically tell you the orientations. And the last one, this alpha, tells you the ratio between eta 1 and eta 2. So it can tell you the shape of these three-body systems. So then we write this kinetic part into a hyperradius part plus a part called the hyperangular momentum part. And this hyperangular momentum operator also have an eigenstate that is called this hyperspherical harmonics. So this is its eigenumbers. It's written as k times k plus 4. So you can write your three-body wave functions in the expansion of this spherical harmonic expansions, so to get the complete wave functions. And so the subscripts for this hyperangular momentums represent by different quantum numbers. So first, the quantum numbers k, and also the angular momentum for the pair particles, and also the angular momentum from the third particle to the pair. And also, when you couple these two angular momentum, you get the total angular momentum and its z projections, right? So it's all the angular, the quantum numbers for this spherical harmonics. And we find that actually, if you have k equals 0, basically the 2 neutrons are sitting in S wave relative to the core. And once you move this k to larger numbers, you have k equals 1. It will be a mixed state of p wave and S-wave neutrons. So it's, for example, if this particle is a core, so this one neutron will be in a P wave, and the other neutron is in an S wave. But if you move this k equals 2, then these two neutrons can be both in P waves. So this is a general picture of this hyperangular momentum. So then we write down the Hamiltonians, right? So you have this the Hamiltonian for each, the kinetic term for each particles minus its center mass motions plus the pair interactions between these three particles. And so then once you project this Hamiltonian into hyperspherical harmonic basis, you have this called hyperradial equations. So you have this kinetic part from the radial part of the kinetic part plus this hyperangular momentum part plus minus this eigenenergy part, right? So then on the left, it's a function related to the two-body potentials. It's written as the two-body interactions connected with this hyperangular, this hyperspherical harmonics functions. And so it will have diagonal parts and also on-diagonal parts. So for simplicity, now let's just focus on the particles have the spinless particles for illustrations. And so now we talk about three-body system in a Borromean state. About so in this problems, then if the three-body systems, you can see from this equation that the three-body systems always have this centrifugal barriers, right? So this part will also give you a centrifugal barriers, even k equal to 0. So unlike two-body system, we know that for two-body system, when it's in the S-wave state, its centrifugal barrier it does not exist. But for here, if you have the lowest state, k equals 0, it still have this centrifugal barriers. And so this barrier goes increasing rapidly with k, because when k increases, this strength will increase. So the practical consequence of this is that once you have higher k's, this part will be suppressed in the wave functions. And so this expansion in this hyperangular momentum k will converge really quickly. So basically, you can describe your wave function using a couple of numbers of k for these expansions. So if we have a short range interactions, say this, if its two-body distance go to R0, the potential go to zeros, then we can see that if you sandwich this between the hyperspherical harmonics, the function w kappa prime will falls off quickly as the power rho times 2, rho to the power minus 2 times L1 minus 3. So it will go, you can see that even when L go to zeros, it falls off faster than the centrifugal barriers from the hyperangular momentum. And so this vanishes this will then vanishes at large distances. So under this limits, the hyperradial equations, originally it's a coupled equations, then it will be decoupled into a single channel equations at large distances. So then we can make this assumption that when you look at asymptotic behaviors, if this is hyper radius r is at a large distances, then you have this single channel equations, and this binding momentum is related to the binding energy in this way. And so now we have these differential equations. You can look at these asymptotic behaviors, and you can see that if this rho go to large distances, it would decay exponentially as e to the minus three-body binding momentum times rho. And if in an intermediate region that when rho is small, then it will have this power law behaviors, right? So now we can basically tell how this hyperradial function will approximately look like in this limit. And you can use this to calculate its mean square radius for these two neutron halo systems. So use this wave function square times rho square times d rho. And so to really calculate this, it's technically tedious. So now I just mentioned that you can separate this integral into small distance parts and large distance parts. And the small distance parts will then give you a finite number. And the interesting part is this large distance part calculations. If k equals zeros, then rho square will go to a log term with a log kappa times rho L. It's a cutoff distances. And if k is not zero, then it will turn into a constant. And this was shown by Fedorov in this 1994 papers. He basically calculated this root mean square radius for two neutron halos and shows that how it changes with the binding energies at different hyperangular momentum k. And it shows that if k equals zeros, when the energy goes to zeros, this hyperradius will diverge to infinity. So basically, it's very similar to what we see in neutron halos, right? If the binding energy is really small, the wave function is very extended. So the two neutron halos can have a large distance separated from the core. And for any other case, larger case, then you see that, and they will converge to some constant values. But at least for k equals 1, the convergence is not that fast. So, but for k equals 2, they converge quickly to a finite numbers. So we can see that will give you a hint why when we observe in these two neutron halos, most of them are in an S wave, or final state S wave states. Okay, so now let's go back to this plot, right? So we already mentioned that you have one neutron halos, and for some of them you have two neutron halos, and basically you can use this formalism to describe the two neutron halos, and most of them they will have this capital K is smaller or equal to 2. So it's sufficient to describe the wave function of those two neutron halos. But later on, I think we will, in tomorrow's talk, I will mention Faddeev formalism that will give you a different picture of how to describe two neutron halos. So now we basically do, I mentioned some properties of this one neutron or two neutron halos. And actually in experiments, there are different ways to measure the structure properties. So there are static ways to measure its mass and also the charge radius using laser spectroscopies. And then you can also use this NMR method to get its magnetic moments or quadrupole moments. And for the you can also use reaction and scattering method to get some dynamic properties and also structures. And for example, you can get its spatial or momentum configurations using elastic scattering or some reaction cross-section method. And so for some details, I will show in the next few slides. So this plot shows the measurements from this reaction cross-sections. So this reaction cross-section can be written as the integral of this transmission functions. And this function is actually related to the mass distribution of this projectile particles and also the target particles. And if you have a stable target, in this case, the target is a carbon-12, you know how its distribution is. Then you use this function and the measured cross-sections at different energies, so you can then try to make some guess of how this projectile distribution looks like, and you do some fittings, then you get this distribution of this projectile targets, particles. In this case, it's beryllium-9, carbon-12, and aluminum-23. And so once you get this matter distributions, you can calculate this mean square radius to get the size of those exotic nuclei. And for normal nuclei, we from the experiment, we can see that it follows this a to the power 1/3 distributions. And so in this, but for halo nuclei, you will see that its root mean square radius, or this called matter radius, will increase really large. And for this plot on the left, it's this matter radius distribution. a matter distribution for lithium-9 and lithium-11. So you can see that for lithium-9, this core, it drops rapidly when the distance r increases. But for lithium-11s, it has a really largely extended tail. So this is different from the normal a to the power 1/3 distributions. And this similar behavior is also observed in helium-6 and helium-8. You can see that the valence neutrons will have a largely extended tail. And so this is give you some examples of this halonuclides this experimentally determined matter radii compared with this general a to the power 1/3 radius for stable nuclei. So you can, from their ratios, you can see that the valence nucleons are largely extended far away. So, and in the measurements, what they see that if they do this reaction cross-section measurements for a chain of isotopes, you will see a big jump once you move the projectile to a halonuclide. This was shown in this paper that measured this lithium isotope. I think this is lithium isotope. Oh, carbon isotopes, right? Once you move to carbon-22. You see a big jump of the reaction cross-section and also its matter radius. And so besides the matter radius, we can also get the charge distribution of the halonuclide. This is normally used in this isotope shift measurement, use atomic spectroscopy method. So in this method, what you really measured is the atomic spectrum, not nuclear spectrum, right? So this is atomic physics measurement. But from these atomic spectrums, you can relate this to equations that will tell you that there are some contributions to these atomic energy levels. So basically, first of all, we know that from the Bohr's model, you get this 1/n² energy levels, right? But then once you add relativistic corrections, you have fine splittings, and then if you have magnetic moments, you have hyperfine splittings. This we know from the textbook. And actually, for those energy levels, you also have some higher correction from QEDs. That's basically from the self-energy of the bound state electrons and also vacuum polarization effects. And you also have higher order corrections from the size of the nucleus itself. Because in the normal atomic pictures, the nucleus is the point particles. But actually, if you have the nucleus has the charge distributions, it will make corrections to the atomic energy levels. So you use these equations, and you can then measure. What you can measure is the energy shift, the atomic transitions, and you use these calculated equations compared with isotope with this atomic transitions. You get this simple equations. This is basically tells you the difference for these atomic transitions in one nuclei to the other nuclei. So normally these two nuclides are in the same isotope chain. For example, you measure the difference between atomic transitions in helium-4 and helium-6, right? So you get these energy differences. The contributions are from one from the QED effects and also nuclear mass shift. So basically changing of the atomic wave functions, and also one part called the field shift is related to the charge radius squared. So this part will give you the difference of this charge radius squared for these two isotopes. And so you can use these equations and from the measured isotope shift to obtain the charge radius. And this is actually the really accurate measurement to determine the charge radius. It's more, normally it's more accurate than reaction cross sections, because with the nowadays laser spectroscopy methods, you can very accurately measure these atomic transitions. So this is the table shows you the charge radii measured in this isotope shift, and you can use this simple equation to transfer this charge radius to point proton radius. And so what we mean point proton radius is that so we know that proton has a size, right? So what you measured for the charge radius is the charge distribution for not just the distribution for those protons, but also the distribution for all the proton, the charge distribution for each protons. But if you subtract out the charge distribution of the proton, you get the relation between these two numbers. So the number on the left is just tell you the distribution of a point-like proton. And the terms on the right will give you the proton size radius of the single proton radius and the single neutron radius. So the size of the proton and neutron itself minus relativistic corrections called the Darwin-Foldy term. And so now you compare this with matter radius, right? The matter radius will then relate to not just the point proton radius, but also the point neutron radius, because for charge radius, the neutron is a chargeless particles, but for matter radius, the mass of the proton and neutron is about the same. So for the matter radius, the neutron also has important contributions. And so now let's use those radius to help you to get this clustering picture in halo nuclei. We know that for this halo nuclei, you have a core and valence nucleon distributions. So let's take one neutron halo as an example. This valence nucleon will orbit the core at large distances. So you can see this is the valence nucleon and this is the core. And so you have the size of the core and also the distance between the neutron and the core. So if you want to calculate the matter radius, basically you need to, this is the matter radius of the whole one neutron halos. So you have the contributions from the matter radius of the core itself, and this RMC, so it means the core matter radius squared, plus the distance between the core to the center mass of these two body systems. Because once you add one neutron, the center mass will be shifted, right? So, and then the neutron will also have a mass, right? So they will make another contribution. So it would plus this distance between the neutron and to the center mass of these systems. So this rho n squared. And we can know that where the center mass is at. So you know A times this rho c equals rho n. So basically it will tell you where the center mass is sitting on this line. And you can use these equations then to determine from the measure the matter radius to this core radius, right? So the core to the center, and also the neutron core radius related to this rho c. And now let's move to the charge radius. The charge radius is a bit different because now the neutron is chargeless, right? So it doesn't make important contributions to the charge radius. So basically, first of all, we move from the charge radius to the point radius to the point proton radius. Then the only contributions are still from the core, but the center mass of this system is shifted. So now the point proton radius of these two body systems is related to the point proton radius of the core particles plus the distance between the center mass to the core squared. Right? So you can use these equations and then also extract this core neutron distance, average core neutron distance from the measured charge radius. So now it can tell you that you have two ways to determine this neutron core radius. And there's another way is from this Coulomb dissolution cross sections. So in this measurements, you can have a heavy target, for example, the lead target, and then if you have this halo nuclei beam coming in, these two will have a strong Coulomb interactions between each other. So this nucleus, this halo nuclei will then be excited and break up into valence neutron and core pieces, right? So they will be in a continuum state. And what you measured is this photoabsorption cross section, and then the most important contributions is this electric dipole strength, and we call this B1. And this is a differential cross section. This differential strength is measured. Then, if you integrate all the energies, you get the total electric dipole strength. And you can, because this E1 operator is actually looks like a vector R, so then you can write this operator as rho c times rho c, and then put the intermediate excited states in, so then you can use completeness or called closures to move this whole complete basis. So then you get basically a rho squared operator in the middle, sandwiched by the ground state. So then this tells you that the total B1 strength is actually related to the radius squared, right? So you will have a formula relates this B1 strength to the core neutron radius in this formula. So this is another way to determine the core neutron distances, and now we can make some comparisons. An example is in beryllium 11. First of all, if you use the reaction cross section to determine its matter radius, and you can get its core neutron radius about 6 Fermi. But if you want to get its matter radius, this core neutron radius from the charge radii, and this can be determined by isotope shift measurements. So this number will turn to 8 Fermi. And so then if you use this E1 strength determined from the experiment, so I think this first one was done by Nakamura-san, and you add this ground state to continuum transitions together with this transition from ground state to this P-wave 1/2 minus state, because in beryllium 11 you have a P-wave bound state. So if you add this together, so you get its total B1 strength, and you can use the formula we mentioned in the previous slide to get its this core neutron radius. We see that these different radius are actually in the same order, but they're a little bit different. Some of the reasons could be that once you connect the experiment to these numbers, the theory can have some model dependencies. So for example, in reaction cross sections, there could be some issues with how you use global model to extract the numbers. And for the E1 strength, it's also related to whether there are some excited states that was double counted or missing in this one, once you compare the series number to the experimentally measured number. Okay, so now then another example is carbon-19. So you also have these three different ways to determine its core neutron radius. For matter radii, you get 6.7 Fermi, and for the charge radii, this is different. This is not determined from isotope shift, and this is determined from the charge changing reaction cross sections. And the final numbers you get it's actually same orders, but the uncertainty is actually quite large due to how you use the model to extract these two numbers. And so it actually can tell you that it's very sensitive to determining matter the point proton radius for these two particles. And for the E1 strength, you also get the core neutron radius about 4.7 Fermi. So these, you can see that at least they are also in the same orders, right? So besides this one neutron halos, if we move to the two neutron halos, the spatial configuration have more interesting pictures, because now you have for one neutron halos, the two of them are always sitting in one line. So what you can get is the distance between the two particles, right? But once you add one more neutrons, you have this two-dimensional pictures, right? They can form a triangle, and the shape of the triangle is what we are interested in. For example, it can form, if these two neutrons are very close to each other, they form this shape called dineutron pictures. So basically, two neutrons are very correlated. And if the two neutrons are very far away from each other, it's called a cigar picture. So 2N and with the thick core in the middle, right? So it looks like a cigar picture. And so actually, in reality, the two neutron halos do not, normally they don't just favor one configurations. And this is a calculation using local shell models to calculate the valence neutron, this valence neutron distributions for helium-6. They find that you can see that it's actually a combination, a superposition of these two configurations, right? So you need to, and in the end, once you average these configurations, you can get the average shape of these two neutron halos, but it can never tell you how the wave function really looks like because it's only an average. But we can still use this to get a rough estimate of how these two neutron halos will be distributed. So for this two neutrons, first we can get its matter radius, and for these two neutron formulas, it's related to the matter radius of the core squared plus the distance from the core to the center mass of the systems. And there will be another term related to the distance from the valence neutrons to the center of mass. So this will be this rho n squared. And for the charge radius, it's related to the charge radius of the core itself squared plus the distance from the core to the center of mass squared. And there will be a small correction from the internal size of the neutron itself. So this Rn squared give you the radius of the neutron itself. And so you can use these two equations to help you to build to basically what is known is Rm and Rc. What is unknown is this Rc and this rho c and rho n. So you can use these two equations to get these two numbers. And then you can then use this, what's calculated for rho c and rho n, to get this distance between the core and the center mass of these two neutrons. So basically, you draw a line between these two neutrons, and the middle will be the center. So from this middle to this core will give you this rho c and n. And also this R and n will tell you the distance between these two valence neutrons. This can also be related to using geometries, right? So basically, if you get this rho c and n, right? So this will be this vertical line, and you will also have the let's see, the distance. Oh, I think I messed up a little bit with this formula. I think this is not 2 plus 2, it's a over 2, right? So basically you draw a point for the center mass here, and you get this distance from the center mass to the middle of these two neutrons. This will be a over 2 times rho c, and the distance from the center mass to the neutron will be this line, this rho n line, and so this will form a perpendicular. This will form a triangle, right? So you can then calculate this third line will be half of this R and n. So you get this distance between the two valence neutrons. And then after that, if you want to get the shape, it can be described by these opening angles between these two neutrons. So it can be written as this formulas because you know this half of this R and n, and also this line. The size of these vertical lines, you can get half of this theta n n, right? The tangent half theta n n equals half of the R n n over this rho c and n. And so then you can use these calculated numbers to calculate the opening angles between these two for these two valence nucleons. Let me see, what time is it now? Oh, there's, okay. So we can make some exercise, right? So you can use this experimentally determine the charge radius and matter radius for those two neutron halos, then to try to extract this core radius from the core to the center of mass and valence neutron to the center of mass, and then build this theta and opening angles. We can see that for the examples are lithium 11 and lithium 6, and you need also input for the charge radius and matter radius for the core particles. So you use these two numbers, 4 numbers, right? So then you get this the opening angles for lithium 11 and helium 6, and the results is about 52 and 42. So it's not either in this dineutron picture or in this cigar picture, right? So it's actually a combination of these two configurations. So if you move further from two neutron halos, you can see that for helium 8, it's these 4 neutrons will also form a full neutron halo state, right? But there will be an interesting question about whether it's a neutron skin or neutron halo. So this actually, there's no clear definition of what is skin and what is halos. But what we can see is that for helium-6 and helium-8, if you look at its valence neutron distributions, single neutron distributions, you can see that for helium-6, at large distances, it's really different from this a to the power 1/3 distribution for the core particles, right? The dashed line is representing the neutron distribution for the helium-4 core, and these last two valence neutrons are further extended. But once you move to helium-8, you can see that it's further extended, but compared to helium-6, the valence neutrons are not largely extended, so they have a small extension, right? So some people will call helium-8 has a neutron skin rather than a neutron halos, and this is very interesting. That because for helium-6 it's a loosely bound state, but once you add two more neutrons, its binding energy will actually increase. It's more tightly bound than helium-6, and so this distributions can be determined from reaction cross sections, and so you can use this to determine its neutron density distributions. And actually, this will be an interesting idea also to compare its density distribution with neutron skin in lead, right? So this, because we know that lead also has a very thin neutron skin. And besides the radius, another important quantity for helionuclei is its quadrupole moments. And the electric quadrupole moment is actually sensitive to the nuclear charge deformation and core polarizations, because for quadrupole moments, you do not have a spherical shaped helionuclei. It will have a deformed shape to form a quadrupole moment. And so the increase of quadrupole moments ratio between the halo nuclei and the core nuclei will give you some idea of how the configuration of these two neutrons are looking like. And for example, if you take the measurements of the quadrupole moment for lithium-11 and lithium-9, you get a ratio of 1.09, so basically 1.1. And if you compare this with the charge radius of lithium-11 and lithium-9, it's also about 1.1. And this actually can tell you some idea how these two valence neutrons are looking like. Because if it's a uniform distribution, if the neutrons are uniformly distributed, suppose you have 11 particles that are uniformly distributed, then let me say in this way. Suppose lithium-9 has a deformed shape, right? So it may be an I missed the minus sign. It's an oblate, right? So it's an oblate shape. And suppose if you add two neutrons, the shape doesn't change. It means that all those neutrons are redistributed and in a uniform distributions. Then you only see an increase of the size. So in this picture, you will see that the increase of the charge radius compared to the increase of the quadrupole moment, because quadrupole moment is related to r squared, right? So if the radius is increased by 1.1, and if you use this uniform distribution to describe the quadrupole moment, you will see that there will be this number squared. So it will give you basically 1.2. But this is what we see. This is different from what we've seen in the measurements of quadrupole moment for lithium-11. What can this tell you is that basically you have a deformed core for this lithium-9, and then you have two valence neutrons that are basically in an S wave far away from it. So the quadrupole moment is mainly still due to the quadrupole moment of lithium-9 itself. These two neutrons do not contribute much to its quadrupole moment. So if you use this, you will see that the increase, then in this picture, you will see that the quadrupole moments, the increase of the quadrupole moments will be the same ratio as the increase of the charge radius. So then it will be proportional to 1.1. So this picture actually, from this ratio of the quadrupole moments, you can also tell you that these last two valence neutrons in lithium-11 are actually in an S wave that's very far away from the core itself. And so now let's use 10 minutes to talk about another important properties for halo nuclei called the beta decay. Because the beta decay is an important probe to describe the halo structures. And there's an interesting phenomenon called this beta delayed particle emissions in beta decays. Because normally it has for those halo nuclei, it has a large Q values, so related to the energy released in beta decays. And so the resulting daughter particles, in this case, is the excited states of boron beryllium-11. From a beta decay, you have excited boron-11 state, and it will have a low separation energies. And because of this low separation energy, it can then emit another particles from its daughter particles. So for this beta decay, you not end up with a stable particle to another stable particles, but you end up with an emission of electron and antineutrinos, and also this daughter particle then will decay emit different projectiles from it. And so from this beta decay picture, you can measure this transition strengths, and use this transition strengths can tell you whether the halo neutrons are in S wave or P wave components. And so now let's see some examples of this beta delayed emission in halo nuclei. One example is helium-6. So it would then, from a beta decay, it will emit a deuteron from it. And this has a small, really small branching ratio. So the probability for this to happen is very small compared to the normal beta decay. But for lithium-11s, it can have many different particle emissions, beta delayed particle emissions. And for this beta neutron, this neutron emissions, and it has a really large branching ratios. And so there are also some other examples. And you can, from this picture, you can see the energy spectrum for this, the parent nuclei and the daughter nuclei, and the threshold for the emitted particles and the rest particles. So for this, normally if you look at the most large probability is this allowed transition, beta transitions, L equals 0. So it can be then using the, due to the operator is separated into Fermi transitions, basically L equals zeros, and if there's, so it's a J equals, delta J equals 0 transition. And it also has this gamma Taylor transitions with delta J equals 0 plus minus 1. So the strength of this Fermi transition and delta transitions can be calculated using transition matrix elements. And it has a formula to relate these transition elements to the measured experimental FT values. Basically, it's measure the lifetime of the parent particles. And F and also this T are some analytic numbers that can be calculated using a beta decay series. So the energy release called the Q values is actually how it's related to the separation energies in this beta delayed particle emissions. And so for for this beta minus decay for neutron halos, you can calculate this beta delayed deuteron emissions. So you can use these numbers to find that it's actually related to 3 MeV minus these 2 neutron separation energies. So this is appropriate to apply this for helium-6, for example. And if you have proton emissions, then it's related to this 0.7 MeV minus 1 neutron separation energies. And also for beta decay, we know that you have beta minus decay and also beta plus decay, and also electron capture processes. And this is the electron capture decay for proton halos. And it's a electron capture then emits a deuteron. So you can calculate Q value is related to 1.4 MeV minus 1 neutron separation energy. And there is a small correction from the atomic energy levels for where this new electron is captured on its orbit. And for this there are two mechanisms for this to happen. The decay, you can have this beta decay through resonances in the daughter nucleus, or directly decay into the continuum states. And so let's take helium-6 and examples. It's beta, this Q value for its normal beta decay is about 3.5 MeV. And if you compare with this beta delayed deuteron emissions, the energy is about 3.0 MeVs. So basically, these two energy levels are very similar to each other's. And so it actually can tell you that this beta delayed deuteron emission branching ratio is very small. And this is because this beta decay can happen not only for the valence neutrons, but also happens for the neutrons inside the core. These two have a strong cancellation with each other. So you have a destructive interference between core decay and neutron halo decay. And so the picture on the right shows you the shape of this this transition probabilities are the function of this emitted deuteron energies for this. And this can basically tell you the three-body asymptotic wave function of helium-6. So this is actually give you some more information of how this two neutron clustering picture wave function will look like. And another case is the lithium-11, and its normal beta minus value, Q value is 20 MeV. And if you look at its beta delayed deuteron emission, this number is much smaller, it's 2.6 MeV. So basically, the beta decay for lithium-11 will open many channels in the middle. Because this value is very large, you have many particle emissions states in the middles. So you will see that, for example, this beta minus deuteron emission has a branching ratio about 1.3 times 10 to the minus 4. And this is two orders larger than what happens in helium-6. And an explanation of this is that this alpha D wave function, two-body wave function, actually has many overlaps with the long-range part of the lithium-11. Probably I write this wrong. It's a lithium-9, right? Lithium-9 and deuteron wave function has many overlap with the tail of this lithium-11 two neutron, this halo part of the wave functions. So the deuteron emission basically happens at the halo of the lithium-11. So the valence neutron decay through beta decay and then change to proton, and then this neutron proton will form into a deuteron. Will generate this emitted deuterons. And so once you measure this transition probability distributions, you will see a quite flat pictures. This will tell you that it will decay directly into the continuum without intermediate resonance states in the middle. So yes, I think that's all the slides I have in this morning. To basically give you some talk about some different experimental observables that can tell you the halo structures and can tell you the properties of this one neutron halo and two neutron halos. And so in the talk in the afternoon, I will then give you some more theory pictures of how to describe these properties. Okay, I think that's
so
it.
Thank you. Okay. Maybe we have little time for questions. I mean, if you want to ask some questions to Chen, but there will be, at the end of the day, there will be a discussion session.
Yes, there will be discussions, yeah.
But if you have, please, go ahead.
I've got two short questions. The first question for the statement that you only find like S&P waves halo, generally speaking. So I wanted to know what you think about like aluminium-22 seen as, magnesium-21 plus a proton. There was a paper saying that, like the ground state is a 5.5 plus. In an extreme shell model way, you see it like as a D5.5 state. And they show that, if you use like the Nielsen model, particle router model, with deformation, there is an interplay between, like the deformation and the halo character, and they could find like a D-wave proton halo. So do you really think that it exists or not? Like,
I mean, I think all those are possible, right? What I talk about in the lecture is a really simple picture with just the two-body interactions.
I agree.
And in this picture, it can tell you why what we found for halo nuclei only will favor S wave and P wave, but doesn't mean other states do not exist. And one thing I think you mentioned is very interesting is the deformation, right? With the deformation, you can have the polarization of the core, and then you have different interactions rather than because the interaction I'm writing is only like a central force, right? So if you have other force with angular momentum dependence, then you can have some different things happening.
Then I have another question about, like I think that was around like slide 35. So when you speak about like this dipole strength for beryllium-11,
yes,
and you compare them with and you deduce, these rho Cn.
Yes.
And basically there was a mismatch between the different models.
Right, I think it's...
here, like at the bottom, 35, I think.
This one, right?
Yeah,
yes.
My question was, like the link that you derive, like at 34, at the side 34, for, from the B1, going from the B1 to the rho, you assume like no P wave like is enhanced, like if you go to slide 34.
Right.
I think, you're right, like no P wave enhanced, right, for the B1, so that's
B1,
bottom equation.
Mm-hmm. So this does not include...
Just at the bottom, so like the direct breakup thingy, so let's say you know B1 and you want to get to rho Cn, and you say like no P wave enhanced, but like if you do, for example, beryllium-11, the ground state, that's like a 1/2 plus, so S wave. And so if you do B1, like the P wave, like the dominant contribution will be coming from the P wave, right?
Right.
So I was wondering, like, using this relationship, like, are you sure that, like, once you compute what you compute, like on side 35, that it does not bring an error there? So
actually, in the talking in the afternoon, I will show in the halo effective field theory how to relate B1 to this charged neutron distances. Basically, if you use only S wave to continuum, you get these pictures.
I agree. So no final state interaction.
No, it doesn't have final state. If you have final state, it will be different. You have additional terms. Right.
Some other question? But remember that, okay, Miko, please.
So this is quite interesting presentation, and could you show me again about in a quarter pole moment,
right?
And page 45 or something like that.
Page.
In the rhodium, so you show up the rhodium isotope is here, and then it's on right hand side. So you show up the isotope, and according especially for the rhodium 7, and the quarter pole moment is also minus 40. It's a very largest value, and in comparison with another one, right? And Q moment, it's minus 40 something. And rhodium 7, right? Yes, it's also and tremendously. It's also larger than another value. So, but rhodium 7 is and a beta stability line in nucleus and the binding energy not so in weakly bound state. However, it's a very huge the Q moment. Do you have any reason why the isotope has a very huge number?
Lithium 7?
Yes, lithium 7.
Why it
Yeah.
has a large...
Yeah. Because you can see that, so in comparison with the lithium 11, it's a larger barrier.
Right.
Yeah. In the case of lithium 11, you saw the explain about how large it is. That is, I understand. But lithium 7 is so binding energy
actually-
is stable, but it's so larger, then I could understand. Do you have any opinion on that?
No, actually me neither. Yeah, my understanding is the lithium 6 might have a D-wave contributions, right? So, but lithium 7, why it has a large D-wave?
Yeah, that is also very
this is-
mysterious because you know it's here it's alpha plus triton.
Right.
So
Alpha
that to
plus
me,
triton,
yeah, right,
yes,
triton.
yes.
So
this
that
is-
to me, the
Right.
maybe so we have so alpha and triton, so the distance is so larger. Then the so valence proton has a so the larger value. That is just I try
Me
to
too.
understand.
So
Okay.
I don't, yeah.
Maybe
Maybe
it comes
Maybe.
from this
Right?
configuration, yeah.
Yeah, that is what I'm
That you
thinking. Yeah.
have the-
But I need to so confirm that the picture is right or not.
Yeah,
That would
alpha
be-
and the triton for lithium 7.
Yes, another one. And then lithium 11, what is the sign? Because in minus
Yes, I
is
think
parentheses.
no, it's a, wait, it's a mistake. It should be a minus sign here.
Minus.
Minus, yeah, both are oblate.
But in lithium 11, parentheses in value cube
Yes.
here. So then it's not confirmed or it's already confirmed?
Yeah, this actually I don't know the details. Maybe I'll look at the paper and we can talk
Okay.
about this in the afternoon. Yeah.
Thank you very
Yeah.
much.
Maybe is it possible that maybe they didn't define the sign of it?
Yeah, this is very important.
Yeah.
Thank you very much.
Any more questions? Okay.
Yes.
But remember to leave for the discussions.
A small one, like deformation. Like, can it happen like in a halo nucleus that like the core is deformed, but the
Yes.
overall halo like stays spherical? Like for example, beryllium 11, there are two halo states. The ground state is like prolate, deformed. But when you look at the AMD calculations of the one minus half is more compact. And so could it happen that, like these two states are both halos, but, the quadrupole moment is way smaller for the 1/2 minus state. So can it happen that, can we understand that as a, deformed core, but the overall halo is still spherical because like the cloud is kind of still spherical? Could that happen?
I think it's, yeah, this might be some reason. So in this, so basically here, this thing, right? So you can use different methods to determine this radius, right? So, and I forgot, yeah, maybe this wait, maybe this one. So so this is basically, I followed this discussion from Tanihata-san's review papers. He actually mentioned that for some cases you can have core polarizations. And also I don't know, maybe this is not directly related to what you're asking, but if you have a E1 transitions, actually you might have an excitation of the core, right? So you can have a E1 excitation of the core, you can have the core polarizations. And this, if you just use this formula, this doesn't describe the core polarization effect. So actually, if you use different methods to do this matchings, the difference can due to either from some unknown or included mechanisms in the series, right? So.
Like adding like the, by core polarization, do you mean core excitation, like beryllium 10, 0 plus, 2 plus, or do you mean something else?
So I remember for lithium 8, you have a core polarization,
Yeah,
right?
okay,
So
okay.
so this can be included.
Okay.
Yeah.
It's okay. So thank you, Chen.
Yeah.
And we are back at 11:15. Now there is the coffee break here. We just go up. And the posters, I think you can already put. Okay. Thank you, Chen. quarter to 11.
One